The first step in this project is to create a Strava API application. I followed the Strava API developer's guide, the getting started guide. So basically run through all this information to create the account, create the app, generate the tokens required to access the Strava data. So as you can tell, there's a lot in here. And then basically follow the API SDK documentation to figure out the commands needed to get the activities, get the activity streams, and get any other data that I need from Strava. So this is basically the documentation I use to create my Python script. This is my API application in Strava. As you can see, these are the number of daily requests I've made. This is information regarding my application, and I can show the client secret and token secret and refresh token over here. To actually optimize the application and optimize the requests, I use Postman to test all the requests that I was making before I implemented them in my Python script. Another useful resource was this Medium page, which went through some additional steps that weren't covered by the Strava documentation. But the Strava documentation got most of it, but this had a couple tweaks to it that further enhanced my ability to access data from Strava. I'm now going to cover how easy it is to create a Cloud9 IDE environment in AWS. So I click on Create Environment, give it a name, give it a description. The description's optional, but I like having it. I'm going to create a new EC2 instance. I actually want a T2 medium for the program I will be running. So I select a T2 medium instance type. I want it to shut down after 10 minutes of inactivity to save money. I click Next, and all of this is fine, and simply click on Create Environment. If we now navigate to our EC2 instances, we can see that a new T2 medium EC2 instance is pending at the moment. So that took about a minute, but our environment is now ready. If you notice, I didn't have to create a new EC2 instance. I didn't have to configure the security group settings. I didn't have to SSH into the instance. I didn't have to set up a Python environment. I didn't have to run AWS configure. All of that is taken care of when you use Cloud9. So let me see if there are any updates that we need to install on this server. So it's basically installing any packages that might have been updated, but nothing needs to be updated. Let's see if we have a version of Python already installed, which we do. Let's also see if we have a version of pip installed. And we do. Next, I'm just going to install some packages that I need for my Python script. So I'm installing Boto 3 so I can connect to my S3 bucket. I'm going to install NumPy and also install pandas. I will also be using requests to communicate with the Strava API. So I'll install the request package in Python. All right, that's pretty much it. I have all the packages I need. And one of the other great things about Cloud9 is that I can upload local files very easily by just dragging them over. So I'm going to drag over some Python files that I have on my local machine, and we can see they've already been uploaded. So this is my full program, but I also wrote a test script to upload the local files in my Cloud9 environment to my S3 bucket. So if you look at my S3 environment right now, we can see that this bucket is empty. If I run this script, it's going to take this activities overview CSV file and upload it to my S3 bucket. So let's just run this, and that took no time at all. And if we refresh our S3 bucket, we'll see that the activities.csv file has been uploaded to the S3 bucket. As you can see, Cloud9 is extremely easy and to be honest, a joy to work with compared to Amazon CLI. I used AWS Secrets Manager to securely store the tokens I need to access the Strava API. Using AWS Secret Manager is fairly easy. I click on Store a New Secret. The type of secret I'm storing is other type like API key or auth token. I can store key value pairs, so I can store multiple different secrets in the same secret. These are stored as dictionary, and in Python you can use the JSON reader to parse out the values, and then you can access each of the secrets using the associated keys. But for my purposes, I just need a plain text secret, so I can say create a secret here, test demo 1 2 3 4 5 6. Next, and I can give it a name, test demo website. I can optionally give it a description and tags. I click next. I'm going to disable auto rotation, but for a very secure environment, enabling automatic rotation every X number of days will ensure that, passwords don't go stale. So all of this is fine. I had to modify this script because it doesn't take parameters, so it has hard-coded values for this particular secret. The other issue I had was the function actually doesn't even return the secret. So using the function as is, you basically get none as an output. So I added that piece of code in here, but I don't know why it's missing in the example that AWS gives. So I can store this secret, and if I refresh, you'll see that I have an additional secret in here, which is test demo website. And if I click on that and say retrieve secret value, I can see the secret value that I put in. The other way to store secrets is through the command line. So I have pre-entered in the command that I want to execute. So it's AWS Secrets Manager, create secret, the name of the secret, and the secrets, which is the secret that I want to store. So if I click on this, it gives me the ARN, which is what's required to retrieve the secret. And if I go back into Secrets Manager, we notice that we have an additional secret, which is the one that I created from the command line. If I go back to my Cloud9 IDE, I modified the function so that it took in two parameters, the secret name and the region name, and I defaulted that to US East 1. And this is where I added return secret, because I do want it to return the secret so I can actually print out its value. Next, I want to talk about my main Python script. I import the packages I need. I include the code needed to use AWS Secret Keeper. I use the tokens provided by Strava to connect to Strava via requests and download the JSON files that they provide, using which I create an activities overview data frame. And this is the part that took me a long time to figure out. For each of the activities in the activities overview data frame, now I want to download the activity streams, which basically is data for every second of the activity. This adds up to a lot of data. For my own personal Strava, I have about 1.5 million rows in the activity details data frame. This takes a long time to download, especially since Strava only allows me to make 100 requests every 15 minutes. So I've built in functions into the script which will download 90 activities and then wait 16 minutes and download another 90 activities. So to go through the 565 activities I have will take close to an hour and a half with the waits included. So to speed up the process, I've included an activity details pickle file from about a week ago already in here. And if you notice over here, I'm going to see if there is an activity details pickle file? If there is, I'm going to load that into a data frame. And then I'm going to go through all the activity IDs in the activities overview data frame and see if they exist in the activity details data frame. If they already exist, then I don't need to download them again. So I'm going to create a list of activities for which I have an activity in activities overview, which was just refreshed, but I don't have one in the activity details data stream. And then I'm basically going to download the activity data streams for only the activities for which I don't already have the stream. So it is much more efficient than having to spend an hour and a half to download all the activity stream details every single time. So let's run this program. The initial parts are very similar to what I showed before, where it's requesting the token, it's receiving the token. It's going to generate a brand new activities overview CSV file, which it will then upload to the S3 bucket. And then it's going to use this activity details pickle file to create a data frame. So you can see that it downloaded. Okay, so it's downloading 27 activities, and you can see all the activity ID numbers that it's downloading. So these were the 27 activities that were in the activities overview data frame, but were not in the activity details pickle file that I primed this program with. We can see that there are 1.8 million rows in this data frame with 15 columns. The sum of the moving time is 1.6 million seconds. The sum of the elapsed time is around 3 million seconds. And it wrote the detailed CSV file. It wrote a new pickle file, and it uploaded both of those to the S3 bucket. And if we check our S3 bucket, we should see those exact same files, and they were just uploaded. So that's basically what this program does. It basically gets the activity overview from Strava, and then it gets the detailed activity streams for new activities from Strava. I initially wrote my Python script in Jupyter Notebooks on my local machine. I had to make a few changes to the AWS version. I'm using Amazon Secret Keeper rather than using environmental variables to store my tokens. I also uploaded the CSV files and the pickle files to my S3 bucket, so I had to add code from bot03 to put and get the files from the S3 bucket. Everything else is fairly similar, except for the UI changes, which Jupyter Notebooks allows for a much better layout. So if I go to my script, so one of the major problems I ran into, which took a while to debug, was if I run this script, this is just a test script, to load and then pickle, this activities pickle file. So if you notice, I got this strange error, and it took me a while to figure out that the cause of this error was these NA values. Lat long is actually stored as an object in the pickle file. So even though it's an object, these NA values were causing the pickle to fail in AWS, even though it works perfectly in the local machine. In order to resolve the error, I had to add the following 2 lines of code. I first had to convert the lat long column from an object to a string, and then I basically replaced all NAs with a null value. So if we rerun this script, this time there should be no error, and we'll see that the data for the following activity now has a null in the lat long rather than an NA. So lesson here is to always retest the Python script in AWS, even if it runs perfectly locally. Now that we have an activities overview CSV file and an activity details CSV file in our S3 bucket, there are many different future steps that can be taken to further this particular app development. Amazon RDS could be used to store the activities overview data in a relational database so that it can be queried using SQL. The sheer size of the activity details CSV file, like 1.8 million records just for my own personal usage. If there were multiple users in there, we can easily imagine that growing to 100 million rows. So Amazon EMR would come in really handy to analyze a data set that large. Once there are multiple users in the activity details or even the activity overview data sets, AWS SageMaker could be run to figure out different types of patterns that might exist between different users, or even the same users, different types of activities. AWS Lambda functions could be used to run calculations. For example, normalized power requires a running average over, let's say, 30 seconds. So AWS Lambda could come in useful for creating calculated values from the static data set. AWS SNS could be used for notifications. If something is a cause of concern or something that the user wants an alert for, when those criteria are met, a notification could be sent to the user. Amazon Alexa can be used to refresh the data and also get daily stats. Another application that I've personally found very useful is Golden Cheetah. It's a third-party open source application to analyze fitness data. So potentially being able to take this data and dump it into Golden Cheetah would be very useful, because that's a large community of open source developers doing very interesting things to democratize the analysis of fitness data. But, these are all steps. There's multiple different directions this app can take, but the difficult step of getting the data is accomplished at this point. I'm happy to answer any questions or feedback anyone may have regarding what I've already coded or my future steps for this project.